All right, everybody, we're going to do today the number E, which I love saying because everyone's like, hey, Zabel, E's not a number. But it is because it's like what we use for pi. It's one of those numbers that we use all the time, so we assign a variable to it. So like pi is 3.14. E is a number as well, and I want you to remember what that number is. So the first thing we're going to do is just talk about where does that number come from. It's the sum of what we call an infinite series. Infinite meaning it goes on forever, and then series just means the sum, like adding up terms. And this is the infinite series that we're talking about. I'm going to see if you can fill in a couple more terms as well. If you follow the pattern, we have a couple more, and this just keeps going. So this is the series that generates the number E. Some people kind of get freaked out by the first one. You could put that in there. It'd be 0 factorial, which is 1. The number of ways to choose, nothing is one way. Don't take anything. But this is the number that, if you keep going, infinitely many terms will give you the number E. So I want you to go ahead and see if you can type this in and see what you get. So grab your calculators. Let's see if we can make this a little easier because nobody wants to grab all those factorial symbols. So 1 plus 1, because 1 factorial is 1. 2 factorial is 2, so that would be a half. 3 factorial. 3 factorial would be times 2 times 3, so 6. 4 factorial. 4 times 3 times 2 times 1, that'd be 24. 5 factorial. That'd be 24 times 5, that's 120. 6 factorial, that's 720, and then we could keep going. So it might be easier to type it in that way. Go ahead and do that. Pause the video for a second. Go ahead and type it in. I want you to see what you actually get when you add those up. And we want to be accurate to the 3 decimal places. So if we come up with this, it should be 2 point, and again, type it in, make sure you're good, 718. This is an approximate value for E. Just like we say 3.14 for pi, 2.718 is usually what we'll use for E, a little bit more accuracy. And E is a number that pops up in all sorts of different ways to model exponential growth and decay as a base. So we use this number often as a base. You're going to see it lots in calculus as well, so it's just one of those numbers that we use a lot. On your graphing calculator, I want to look at a couple different options that you have to be able to use for E. One of them is above the divide symbol. So if you do second and then the divide symbol, that gives you E. So if you ever forget what the number is, you've got it. The other one is above the natural log key. So if you do second natural log, you get E to a power if you need it as a power. And like for us, we just did E to the first, and we can get that number that way as well. So it's kind of nice you have that accessibility on your calculator. All right, so speaking of that, I want you to go ahead and think about what the graph of E to the x would look like. So if you're actually graphing this equation now, I could rewrite it like this then. We know that this is a number, and we are raising it to the x power. So it's really just a base, right? When we're thinking about that equation, e to the, it's just 2.718 raised to the x. So it's a base being raised to a power. And the base is bigger than 1, right? So it's going to grow. So this is going to definitely be growth. And if you think about it, you know what 2 to the x looks like. And the relationship with 3 to the x is a little bit steeper. So 2.7 to the x is going to be somewhere in between what 2 to the x looks like and 3 to the x. So you can get a really good picture in your head of what that is. And then what would its y-intercept be? Well, anything to the 0 power, right, if you put in 0, is going to give you 1. So we can get a really kind of good gut sketch of this. To the first power be 2.718. And is it going to have an asymptote? Well, sure. It's going to get closer and closer to 0 the smaller x gets. So we can think about what those values would be. I did it on my calculator too, so I could take a peek. I just went into y equals and I did e to the x. So using your second natural log key there. And then take a peek at the graph. We know what that's going to look like. And if you want more ordered pairs, we'll go into your table. We got a bunch of values then we'd be able to see to be able to do that. So these work exactly the same as what our graphs did last week that we talked about for regular bases raised to powers. It's exponential growth. It's a percentage growth. So think of your base as being that 2.718. Now this you can move up, down, and left and right. You can stretch it, shrink it. You can reflect it. We can do all those different things. Because remember, if we add or subtract outside a constant, that's going to move the graph up or down. If we add or subtract up in the exponent with the x, that's going to move left and right. If we multiply by something out front, so out here, that's going to stretch or compress. So we can do all of those same things we would normally do with any other parent graph because it's just like 2 to the x. So let's talk about 1. I want to see if you can figure out what's happening in this particular graph. So take a peek at what's being happening here. Our normal graph for e to the x would look like this. So maybe it's helpful to think about what that did. So what happened to our new blue graph? Well, it looks like it was reflected over the x-axis because it's below, but it was also reflected over the y because of the direction that it's going. If I just flip that green graph down, it would be doing this, which is definitely not what I have. It's that flipped as well. So actually, it's reflected over both. So which of those equations show both? Well, it would have to have both negatives. The one out front is the reflection over the x-axis, and the one up in the exponent is the one that's reflecting over the y-axis. So those reflections can happen in our graphs for e to the x as well. They're just regular base being raised to that x power. So I want you to compare this exponential growth or decay in terms of e to what we had before. What we did last week was this. We had y0, and then we had 1 plus or minus the rate, and then to the time. So we talked about a rate and decay of something like this. So what we're doing is we're replacing this part of it right here with this part right here, this e to the k. So instead of saying 1 plus or minus r as my base, I'm doing e to a power to give me whatever my base is going to be. But everything else is exactly the same. The final amount, the initial amount, the time in whatever makes sense. So it could be time in minutes, it could be years, whatever. But I'm replacing the 1 plus or minus r with e to the k. So I'm replacing that. And you can actually model anything that grows or decays exponentially in either of these forms. So we're going to compare next week. We're going to talk about, does it really matter how close are they really? They're pretty close. They'll give you very similar values. So let's think about what kinds of numbers we have to do. In our old form, we'd either add the rate if it's growth or subtract the percentage if it was decay. Very similar here, but let's talk about what the k has to be to make that happen. So if you raise something to a power, if the power is positive, you're going to multiply by it. So for example, if you do e to the second power, where it's a positive exponent, that means you're timesing e times itself twice. So e times e, it's a multiplication. If the exponent is negative though, like if this k value were negative, what does that really mean? Well, that's 1 over e to the second, which really means in effect that negative exponent means you're dividing by e twice. So if you want to have growth, what kind of scenario do you want? Well, you've got to be multiplying by something, right? So the k value has to be positive if you want growth. And if you want decay, that k value is going to have to be negative. So you're going to have something less than 1, a negative exponent. So you're actually dividing by e that many times. So that's going to give you something that gets smaller and smaller and smaller. Again, can't quite get to 0, but it would have had that same decay kind of asymptote, the positive x-axis. So we think still about it's kind of like just adding and subtracting before. It's positive plus if it's growth, or it's minus negative if it's decay. So it works very similarly. It's just with a base of e now instead of this 1 plus or minus r. So let's just talk about just like a general scenario. What could this look like? So if you had an equation that was modeled with this, what would that tell you? What kind of a situation would this be? Well, what does the 6,000 tell you? Well, that means it's starting at 6,000. That is the starting initial value. So whatever you're beginning with is always that y0. So whatever it is, people, money, it's going to be 6,000 as that starting population. And then what does this tell you? Well, it's positive, which means we have growth. And what percent growth would it be? 0.06? That's 6%. So it's a growth of 6% per, and I'm just going to say ... I don't know, right? Because it doesn't tell me, but it could be per year, per month, per day, depending on what your scenario is. So we can tell so much information just by knowing what those values are in the formula. All right, so let's try one of those. So we're going to look at growth of a population. So population is kind of a tricky one because there's really so many situations that it's necessary to know what's happening in a population growth. So for example, infrastructure, hospitals, schools, roads, bridges, fire department, police, all of that is really predicated on knowing how many people you're dealing with, right? So to be able to model accurately population growth or decay, depending on what it is really critical. So there's a lot of people where their entire job is mathematical modeling to help do these projections, taking into account all the factors that might need to be for that. So this is a place in California, Bakersfield, California, that back in 1950, they did this projection model to model the growth of their population. So tell me, based on that equation, what the population was in 1950. Well, it would have been 33,430 population in 1950 because that's my starting value. They say years since 1950, that's my y0. Okay, tell me what's happening to the population. What do you know? Well, look at your exponent. Excuse me. It looks like it's growing at 3.97% growth, because it's positive, in population. Try to make this as in population per, and what's our unit of measure? Well, it's years, right? Years since 1950. So we're growing at almost 4% per year. Now, most places do not grow in population exponentially. It's usually a much more gradual thing, like linear growth, a constant rate of change. Exponential growth is where there's a percent change. It's a multiplication factor each time. It's growing much more quickly. So even back in 1950, Bakersfield had bigger population than Hastings did. Even then, obviously, because Hastings now is about that. So it's a very different kind of situation. So could you use this model then to project what the population in Bakersfield would be in 1955? Well, sure, we can project what it's going to be in any year. We just have to figure out what t is going to be. So the way they decided it, instead of putting in 1950 for their initial starting year, they just put it in as year 0, year since. So 0 is 1950. So 1955 then would be a t equals 5. People do that a lot because who wants to start a graph at 1,950, right? Think of the scale. So if I can put in 1950 as 0, it's going to make my life a lot easier when I do that calculation. So we know what we're starting at. We know what our rate of growth is. And if I want it for 5 years from then, I can just go ahead and put in a 5, and we can get our approximate population. So you can go ahead and type that in. I tried to jot down what the numbers were, at least pretty close, so I can get it at least rounded to the nearest person here. You don't want to be that point whatever. So we'll round it to the nearest whole, because if you're going to drive into the city, welcome to Bakersfield, California, population 40,770.29. You don't want to be the 0.29. So let's just round it to the nearest whole. That probably makes more sense. That's one way to do it. Now, some other people, though, might type in this original equation into their graphing calculator, right, and then go into their table and look at x equals 5. That could also be a way that you could get that. And the cool thing about using the equation, or the equation, help me, the equation on your graphing calculator, get that all together, is that you can do it for any time, right? So you can do projections for any year that you want. So, for example, if they were projecting out to 2015, then in your table, what t value would you be looking for? Well, how many years is 2015 from 1950? That would be 65 years. Or you can go back and do it how we did the last one. Go ahead and just type it in using that model, and we can put in our 65, whichever way you want to do it, and see if we can come up with a population for that. So it's pretty big. I think it's 421,000. I don't remember what the number was off the top of my head. I think it was something like this, 767, somewhere in that ballpark. So over 420,000 certainly. Now, if you Google, and go ahead and do this right now, if you Google Bakersfield for current day, so the closest we can get, Bakersfield current population is somewhere, there's been different numbers that we've seen today, in like the 350,000 ballpark. Some numbers have been bigger, some have been a little bit smaller, but they've been right around 350,000. So the projection was this, the actual was that. So how do you think they did? Well, considering they did this model 65 years ago, lots can change in 65 years, I don't think it's that far off, really. But it didn't keep up. The growth did not keep up as much as what they thought. And this is a really important thing about models. When you have a model, they can change, right? It's not infinitely for all time will this town continue to grow 4%, because you cannot do that for all time, right? Because eventually you're going to run out of space, both land, resources, jobs, all of that. You cannot be able to continue to have exponential population growth in any place in the world. So it's a very kind of constantly changing situation. So when we think about the models, we have to adjust them. So over the course of time, they would want to make some adjustments to this model. Obviously, the growth rate isn't keeping up. Maybe it's not even exponential anymore. Maybe it's changed to a linear model. We can look at the graph and determine that and then make a new projection. So really important to think about that we use modeling all the time, but the models change. All right, so let's take a look at something we talked about before as well. We had an equation before for compound interest. We did a formula that looks something like this for things like savings accounts and be able to figure out what that looks like. Now, again, if we make a replacement here and we replace now, if we could compound interest as often as we possibly could. So what they call continuously compounding interest. Like remember, the more often you compound interest, the better it is for us, right? Because they put that interest into your account, you earn more money, it's great. If we just continually compound interest over the course of time, we're going to get more interest. Our account balance will be better. So this is sort of the best case scenario, this PE to the RT formula. Everything means the same. So the principal, the rate, the time. We're replacing out this base, though, with our e to the instead. And I want you to see how that affects your final answer. So if you could actually, in effect, compound continuously, which we know banks can't actually do, this would be like the best case scenario, like the limit, like the most it could possibly be would be compounding continuously. So it's the most often. So I just want you to see, first of all, how the formula works, and then we're going to do a comparison. Is it really better? Like how much better is it when we do continuous versus say monthly or quarterly, something like that? All right, so here's the scenario. We're going to try to find how much would be an account after 9 years they're saving up for a college education if they're starting off with 31,500 and a pretty conservative interest rate, but 0.076. And then we're going to put it in there. If you just said T, we could look at their account balance over time. But we want specifically in 9 years, so I'll go ahead and do it just for the 9 years. But again, if you graphed it on your calculator, you could see it for 1 year, 2 years, 3.5 years, 28 years, you could see the whole thing. So their account balance at the end of this particular amount of time was 62,000. Try typing it on your calculator yourself. $426.36. So you pretty much doubled your money in 9 years is what that would be saying. Your investment was 31,500. We're almost to double what that would be after 9. So it's the rate and the time and that initial investment. So a pretty decent interest accumulated over that amount of time. So let's do that comparison then. How much better is it really when we do a comparison of compounding continuously? So we'll do continuously over here versus we're going to do quarterly, but you could compare it to anything you wanted. We've already said and we know that the more often you compound, the better off you're going to be money-wise. So let's see what that truly is. So let's start with the continuously. So this guy, he got a signing bonus when he was hired out of college of $7,000, and he decides just to put it away into a retirement account, a savings account, so he can save for the future. And it's a pretty moderate savings account, so 5.25% interest, and he's going to put it in there for his entire work career. So he's planning on working, say, like 35 years. What we want to figure out then is what would be in his account if he was compounding continuously. If his bank that he did this investment in compounded continuously, what would he come up with? Go ahead and try typing that in. So $43,965.72. Did pretty well. Remember, like his initial investment was only $7,000. He's up to almost $44,000. So pretty decent amount in interest there. So how much better than quarterly is continuous really? So we're going to go back and use our regular account balance that all of us are dealing with on a regular basis here. And let's see how much better it really is. So we still have our same initial investment. Instead of e to the, I'm going to replace it with my interest rate divided by how many times. Now quarterly, that would be 4 times per year. So n would be 4. That's what quarterly means. And how many times are we going to do that? Well, it'd be 4 times 35, right? So 4 times a year for 35 years. So what's the big deal with continuously? How much better is it really? So try it. See what you come up with. I got $43,443.27. So ultimately, if you subtract them, the difference between the two is $522.45. So it's only about $500 more over 35 years. It's still more though, you guys. It's still better, but not that much better. If you look at the difference between, say, quarterly versus monthly, again, not that much different on a small account like this. Now, obviously, if you're talking millions of dollars, it could be more money, but that's kind of the same. It's the same percent, right? It's the same comparatively speaking. So it's really not that big of a difference, but it is definitely more. The more often you compound, the more interest you'll earn and the more principal you'll have. Now, the last one I want to talk about, and this is kind of a cool thing to look at. Get it? Newton's law of cooling. It's really cool. Good joke. There's a lot of things like that. I could have said you're really interested in the last one. because it's compound interest. Yeah. So bad jokes. Sorry. So anyway, Newton's law of cooling is a great example of something that uses E. And there's a bunch more in the assignment as well. Really cool things about like percent of how much knowledge you remember after a certain period of time is exponential using E. There's lots of different things. But we're going to talk about Sir Isaac Newton here and his law of cooling. So anytime you take something that has a temperature and you put it into a temperature that's cooler than it, it will cool down till it reaches that temperature. So it's going to cool down as an exponential decay kind of thing. So when you think about what the graph would look like, it's going to be doing something like this. Now, what's really cool, I keep saying that, what's really interesting when you look at Newton's law of cooling is if you look at the equation, you can tell a lot about what the graph's going to look like. So let's talk about this part of it, the plus C. What does that do to your graph? Well, it moves it up C units. So when you think about this decay, it's going to be at that value of C. You're never going to get cooler than the surrounding temperature. So that horizontal asymptote that gets shifted up is being shifted up to the value of that number. So if you've ever wondered why that is in that situation, the temperature of the medium surrounding it. So for example, if you take something out of the oven that was at 400 degrees and you set it on the counter, which is 70 degrees, room temperature, whatever, it's going to cool down to that 70 degrees. It's going to be exponential decay. But it's never going to get cooler than that 70 degrees unless you move it someplace cooler. The Y value, final temperature, kind of makes sense, the temperature of the object over time. Let's talk about the negative up here. What do you know about negative exponents? Well, that means decay, right? Negative constant, that means we're dividing by e to that power. The numbers are going to get smaller, so it has to be a negative exponent. T is time, obviously. The K is the constant of cooling for the object. It's pretty easy to measure these. You just have to take a timing of it, so you know what the temperature is originally, you know what the temperature is after a particular period of time. You just take the temperature, and then you can calculate the constant of cooling, which is what people have to do to figure out these things. And then the A value, let's talk about that. This is the most critical piece, I think, of all of this. That's that kind of stretching or shrinking idea, kind of that steepness part of it. A in Newton's law of cooling is the amount it has to cool. That's really the easiest way to think of it. So if you're starting at 400 degrees and you're going onto the counter at 70 degrees, you have to cool down 330 degrees to get to that room temperature. And that's what A is. It's the difference between the starting temperature and then the surrounding temperature, where it's going to end up. How much is this guy going to cool down? So it's that stretch or compression, that A value. So that's kind of what the initial value is. It's how much is it going to cool down, because you don't have to go all the way to 0 every time, right? It's going to go all the way to whatever C is every time, right? Which is why it's not the y-intercept just straight up from 0. It's from the C value. So it's the amount that it has to cool down. So that's where that A value comes from. So true story. I bought a whole bunch of pop for an event, about 12 cases, put it in the back in the trunk of my car. So I bought this at Cub. It was 70 degrees in Cub. It was lovely. Went out. It was January. It was disgusting. It was 15 degrees outside. And I put the pop in the trunk. All right, so what would the temperature be of that pop in my trunk after 30 minutes if the constant of cooling was 0.05? Would my pop be frozen? All right, let's see what you think. Plus C. All right, so the amount it has to cool. So it's going from 70 degrees in Cub down to 15 in the trunk of my car. So it has to cool down 55 degrees. So that's the amount it has to cool. That would be like that y-intercept. So it's going from the starting temperature down to that C value, whatever that surrounding temperature is. My constant of cooling is 0.05. I've got 30 minutes. Now again, if I put the T in there or the X, I could graph the equation and I could look at my temperature of my pop over time. I could actually look at the graph and see what it would be after each amount of time, where it would be at. And then the constant that it's going to be going into was 15 degrees. The surrounding temperature was 15. Don't forget to add that on there, because that's the coolest it can ever be. Now, if you do that calculation, try it on your calculator, you should get about 27.3 degrees. So after 30 minutes only, just 30 minutes, that can of pop is already below freezing. It's under 32. Now, if you leave it in there even longer, then it's going to get frozen solid. And if you've ever done this, if you put a can of pop in the freezer just to get it cold because it wasn't cold, and you forget about it, guess what happens? When that can freezes, the stuff inside freezes, it expands, and then what happens to the can? Blows up. So what I had was like the 4th of July in my trunk, 12 cases of 24 packs of pop, Diet Coke slushy everywhere. Math is real, people. there's things you need to think about. So be careful. Newton's law of cooling, it's a thing. So be careful on this. We know things like this happen, but kind of a cool situation to think about when we can look at an actual real situation that's being governed by these laws that we know, and then we can make projections based off of that, and that's where the real power comes in. So just don't forget to bring your pop in from the car, or take it out of the freezer if you're cooling it off, because stuff happens. So be careful. All right, so e to the x, it's a number, e 2.718.